Hi everyone, welcome back to the afternoon session. We're starting off with Misha Belkin at UCSD, who's done a ton of super important recent work on sort of feature learning, on understanding generalization in its many forms, especially double descent and more recently grokking, which I think is most important we're going to be hearing about today. So, hand it over to you. Thank you very much.
Thank you very much. Thank you. So this wow. Is there some way to? Oh, yeah. I would like to talk about this kind of idea of emergence and grokking, and in particular to argue that we need to understand what happens even in very simple architecture. Well, simple should be really in quotes, as I put it there. One thing I would like to do, it overlaps somewhat with the talk that I gave at the boot camp. So I'm very happy to stop and take any questions and sort of make it as interactive as you would like, especially given that this, many of the things are quite speculative. Okay, in any case, so this workshop is on computational models in transformers. And what is transformers? Well, it's an attention plus an MLP. And there has been a lot of very nice work discussed about attention. And I would like to argue that we also need to understand what's happening in MLP. And in fact, our understanding of MLP is rather lacking. So I don't think it's possible to understand what's going on without some form of understanding the MLPs. And what has been observed recently is that some really remarkable properties which were observed in these new systems can be just purely observed in very, very simple, like two-layer neural nets. And in some sense, well, so, okay. In some sense, okay, you can say that MLP already can implement any function. So that there is this tension, right? Because in principle, yes, MLP can implement any function. So if you just say something in an MLP, that's not very useful. But of course, we know that what is being learned is just not an arbitrary function. And so maybe the goal is not understanding MLPs as such, but to understand some sort of inductive bias in MLPs. Furthermore, I would say that even like two-layer MLP maybe is too complex, and we need even simpler models. And I would argue that recursive feature machines is actually a model which is, for various reasons, simpler and probably easier to analyze and easier to use as well in many cases. Okay, so what's emergence? Well, when we think about emergence, this is a kind of typical picture, right, of metamorphosis. You have a larva, right? It becomes some sort of cocoon, and then a butterfly emerges out of that object. Now, what's interesting here is that there is a discontinuity, right? There is a butterfly which doesn't actually resemble at all the larva, right? You have now, from an external point of view, this is a very dramatic transformation. You can, of course, maybe like take an X-ray and try to see what's going on inside the cocoon, and you can see that there is some sort of continuity, but that's not a continuity which is reflected externally by what you can observe here. So I think that's actually maybe not a bad way of thinking about what's happening in this model, right? We're observing something, and then we see that something changes dramatically. And I guess the question is like, what's the analog of an X-ray, and can we understand what's happening inside the things? Sort of what are we dealing with in terms of this phenomena in large language models? This is one of the examples of this. You have a number of parameters. And as you're increasing the number of parameters, certain scales seem to undergo a dramatic transition from essentially being at some sort of random guess level to like very good performance. The same thing can be observed with respect to the model scale in terms of the training number of training operations. Okay, so what you see is that if you train the model for some amount of flops, you don't get good performance for things like maybe modular arithmetic or some other tasks. And then like at some point you have this sharp transition that the model actually learns. Okay, so that's what are the key variables here? Well, so we have emergence, and this emergence can be like, with respect to parameters, with respect to data size, and with respect to compute. These things are closely related, and often actually in kind of this modern discourse are used interchangeably, but they do have different properties. And in fact, I'll give an example when the data size and compute somehow don't behave the same way. Like for grokking modular arithmetic, you can actually see examples where they're quite different. Now, like there's been quite a lot of work trying to connect this quantities and in some way trying to understand, but I don't know. Again, this is very unclear. I think what's really happening and whether this how valid these connections are for, especially in the context of this emergence type of phenomena. So from a historical point of view, I think it's interesting to think like, like we probably have always known that more data is good. Going back maybe thousands of years. More parameters is good is kind of an interesting thing, right? I think probably was first observed with boosting. And I think compute is good maybe also with boosting. I'm not sure, but it's, so that's maybe like 30 or 40 year old. It's still not really new, but it's much, much more recent, this understanding. Okay, so I kind of maybe first try to suggest that there may be like different types of emergence. And then I'll specifically discuss grokking. That's a sort of plan for this talk. So what are the different types of emergence? And one, maybe we can call it compositional emergence. And oh yeah, I should say like, okay, that there have been, before I discuss that, is emergence a mirage in some sense at all, right? So there have been some arguments made that emergence as such comes from some sort of discontinuity between some sort of true underlying measure in maybe something like the test loss and what we observe, which is a discontinuous measure such as accuracy. And perhaps we're being kind of misled by the metrics that we impose to judge progress for this system. And I think it's reasonable to think that at least for some of those, it is true that this is accurate. But there are other transitions which seem to be true emergence in the sense that there is no obvious measure, and all our progress measures are kind of hidden, to use a term from, I think, okay, so what you can think about like a compositional emergence. There have been actually quite a lot of recent work trying to, argue that certain tasks are compositions of smaller, maybe kind of atomic tasks, and you can kind of think this is a nice picture from Boaz Barak's blog. If you have say runner, right, and they need to do hurdles, and they need to do like 10 hurdles in a row, then the probability of them completing a race is kind of discontinuous with in terms of the probability of doing a single hurdle, right? Because the probability of completing a race, if the probability of, successfully clearing a single hurdle is p, then the probability of doing this k times in a row is p to the k. And p to the k, as p increases, actually kind of sharply increases when it's close to 1. Right? So you have a graph, like if you have 1, and you have something like this. So it's essentially discontinuous. And if you're, of course, observing the outcome of a task, you would see that there is some sort of discontinuity, but that discontinuity doesn't maybe come internally from the task itself. This discontinuity comes from a composition. So that is one thing. Another thing, you can kind of think of emergence as a benign overfitting sort of effect. And this goes, I guess, back to the margin theory, this type of example. So imagine that I'm trying to separate this data points, right? And the big circles is the data that I observe. And the small circles, so this is the big circles are training data, and small circles are test data. And what I would like to do, right, I would like to separate the training data, and maybe that's the separate I found. And you can see this gives you 100% accuracy on train. But as you keep training the thing, you're probably minimizing some sort of norm, or maybe maximizing margin, something like that. And what you would see that, maybe after iteration 10, you already have accuracy on train, which is perfect. But after, maybe 1,000 iterations, you minimize the loss, you minimize the norm, and you can see that you're doing much better on the test data. So you would see that your accuracy continues to improve even after, I'm sorry, I should say your test accuracy, your test loss will continue to improve even after your train accuracy is perfect. Again, this is not a new effect. This has been known for quite some time. And the sort of idea of benign overfitting is exactly this type of. Now, grokking seems to be a little different. And let me first describe the sort of this particular picture, and I'll talk more about that specifically. So what you have here, you're trying to predict the outcome of modular operations, in this case, modular division. So you have P1 and P2, and you want to figure out what P1 divided by P2 mod P when P is some primers. In this case. So a couple of observations about this graph. So the red one is train and the green one is test or validation. It doesn't really matter. First, test improves long after train is perfect. And well, this actually is not that different from the previous picture. You can see it's exactly, well, not exactly, but it's very similar. And second, there is a fast transition from low to high accuracy. Again, I mean, what's a fast transition? Well, this is a log scale, so it's not completely that the transition is that fast. Yeah.
You keep changing the model?
Well, because you see, this is accuracy, but you're optimizing a loss. So even when accuracy is 100%, your loss is not 0, so you can just keep doing it. And if, like for continuous losses, it's never going to be exactly 0. So in principle, you can run it indefinitely. And you can kind of think that something similar happens here too, right? If you go here, like your accuracy is already 100%, but your loss, like say you're doing hinge loss or something, is not going to be perfect here, and you can still continue optimizing the hinge loss.
Yeah, I think it's
small but important correction. It's not the continuity is not enough, because if you're using a continuous loss that actually converges to some finite point, it sure will continue changing it, but it's not going to do much. And what's important here is that you're optimizing the hinge loss, the logistic loss, which you never does not attain the minimum anywhere. You can't converge to minimizer. That's, I think, crucial for that.
Well,
It's been observed with other loss functions. If you use certain types of regulation as well, but something in that vein, yeah.
that's a subtle point. I would maybe rather not go there because it's a little orthogonal to. But you can. I mean, it is true, of course, that when you're minimizing the square loss, for example, right? Once your square loss is very, very tiny, that's it. But even for the square loss, right, your square loss may well be here. So you may see the same thing with the square loss. Okay, in any case. Okay, so now is this of that form? And I would actually argue that this grokking phenomenon is not of that form. It's something else. Something else is happening there. It's neither a composition, nor it is this kind of minimizing the norm, maximizing the margin type of phenomenon. So this one is not a mirage. Okay, so maybe let me go over this, and I apologize for those of you who have already seen this. So maybe one way, just very quickly, one way to think about neural networks is just that they learn, and we can even think about a two-layer MLP, they learn some sort of filter, which is given by this W1 matrix, and then they do something on top of that filter. Okay, that's about it. So it's matrix multiplication, some nonlinearity, and then something on top of that. So in some sense, the key here is that this W1 should be thought of as a filter. Okay, it does some sort of filtering of the input space. And what you do on top of that, it doesn't matter. In fact, you can use a kernel. And the key object here is this average gradient outer product. And sort of that the argument is that what you want to learn, the filter that you want, ideally, and when I say ideally, let me actually clarify this a little bit. So what do you want, right? If you would like to predict, so suppose you have a task, right, and you have some input, and you would like to predict some output of this. What would you like to have, right? You would like to, if you are to reduce dimensionality, so somehow imagine I want to find some features which will be the most predictive for my outcome. What would those features be, right? I want to basically ignore features which don't affect my outcome, so I want to kind of decompose my space. So this is, imagine this is my space, right? And I can say, well, these are irrelevant features. So these features don't affect my outcome at all of my predictor. And these are relevant features. So if I have a vector, and I want to classify whatever that thing is, I should ignore this one, and I should, use the projection onto the relevant feature as my input. Now, if somehow the direction of relevant features is, imagine my relevant feature is just one direction, right? Then I reduce dimensionality from one. So if I somehow magically know the features in advance, the relevant features in advance, then I reduced my problem from whatever the initial dimensionality was, which is, could be very high, to simply one. Okay. Now, how do I measure something like that? And if I think that my feature, so here is a kind of important assumption here. Suppose the direction of this relevant features doesn't change in the space. So potentially you can imagine that for this input, these features are important. For that input, those features are important, and so on. But suppose there is some sort of space of features which are important sort of universally for all inputs. That's an assumption, of course. That's not necessarily true. Then something like this would probably be perfect. So if I have a function f, I would like to see which direction have non-trivial gradient with respect to the input. So this gradients are with respect to the input. Okay, so I'm just looking which directions affect. So this matrix, which is the outer product of gradients, encodes directions which affect the output. So for example, the 0 set, the kernel of this matrix, will not change the output at all, and I can completely ignore them. It's sort of from a practical point of view, if you can construct this matrix somehow and take its top eigenvectors, those are the features that you care about. It's actually a strict generalization of principal components analysis, but principal components analysis is unsupervised. This is supervised. So for example, if you have a multi-index model y equals f of mx, then the top eigenvectors, so imagine that m is low rank, then the top eigenvectors of this matrix are the same as the range of m. So it's exactly what you want. Okay. Now, you can kind of think, why is this, like, you can look at the same object locally, and you can see that that gradient outer product is simply a projection onto a linear approximation to your function. So if you take your function, you write down the first order Taylor expansion for this, then the derivative term of that is a piece of that matrix. Now, what you're assuming is that all of the things somehow align. Okay, they all span in a low-dimensional subspace. Okay, so why is this important is because, in some sense, what we argue is that that's what neural networks do. They learn actually this, at least, MLPs do, that they learn this object. So, an example, you take a very simple model, just an index 2. You take the sum of the first 5 coordinates and the sum of the next 5 coordinates. That's an index 2 model, because it just depends on the 2 directions. You take the W1 transpose W1, which is the weight matrix of a trained neural network. And you can see that the AGOP, which I defined there, and the W1 transpose W1 kind of have the same form. And furthermore, this is key if you just forget about the neural network. You train the neural network, you extract these 2 filters, you apply these 2 filters to data, and based on just this filtered data, you can use either a kernel or neural network or any other method that you want, and it will be just fine, with far less training data than the original one. Any questions about this? Okay. So now basically the claim that we made is that those 2 matrices are the same. And I want to move forward to actual grokking because that's the key. But before that, I need to define what this recursive feature machine is. So recursive feature machine is the following thing. So you kind of bootstrap this process of evaluating the filter. So first you build a predictor, which we use a kernel, but in principle, you can actually use anything here. You fit your data, you extract this matrix, and then you re-filter the data using that extracted AGOP, and then you repeat the process. Okay, so it's iterative method, somewhat similar to expectation maximization. Okay, now and maybe I'll skip this, but basically you can see that the results of feature learning are very similar whether you do networks or neural networks or recursive feature machines. But interestingly, you can do even something more complicated with this, and this is from a paper by Ador. This is for neural networks, not recursive feature machine. You can kind of see that you get some very emergence-like behavior when your function can be decomposed into this complicated, well, increasingly more complicated parts, right? So you start with Z1, it's a polynomial with Z1, and then you have some product of monomial Z1 to Z5, and so on. And you can see that, like, after some time, you learn one of the things, then you learn the next one, and so on. So again, this is maybe what you would call sequential emergence, maybe not so different from this kind of the hurdle that you have to pass, right? Except in this case, the hurdles have to be passed in a certain order because the learning the first polynomial actually helps you with learning the next and so on. Okay, now let's get back to modular arithmetic. Okay, so now what underlies this curve? And there was a paper by you cannot see the name, I think, by Andrei Gromov, who first he showed that you can. So the original paper was using a transformer, but he showed that you can use the same. You can get the same result with just a two-layer neural network. And also he showed that the losses, right? If you look at the train loss, so this is the train loss, the blue one, and the orange one is the test loss. And you can see that the test loss doesn't actually go down. So at the very least, from the test loss point of view, it's impossible to see that something interesting is happening here. So clearly, it's not just that you can look at the validation loss and see that this is happening. Now, okay, what's the problem here? First, what you want to learn, you want to effectively fill this table. This is modular arithmetic mod 3, right? A is 0, this is 0, 1, 2. 0 plus 0 is equal to 0, and so on. Okay? And you basically want to fill in these question marks with, A, B, or C. Of course, in practice, the table is much larger. Actually, I asked ChatGPT to produce this table. Like, it took one query. I was going to do it by hand. And it just does this. Kind of amazing. So now, what are the training data? You have inputs, which is, so if the size of modular arithmetic is mod p, then I have one hot encoding of the first element and the second element, right? So b equals 1 would be this, and c equals 2 will be that. And then the label will be the vector which encodes a plus b. Okay. And in principle, you can have p squared total examples. Notice this is, by the way, quite different from something like a multi-index model, because in this case, the total number of examples is finite, right? If you don't learn from all of examples, then you just don't learn. Like if you don't learn from like all examples but one, something like that. There is no, in some sense, there is no asymptotics. Okay, now what are the key questions here? First, what algorithm do neural networks implement? Yeah, Matthew.
Finite, would you not say that it's similar then? So you have a multi-index function where it's Hermit.
No, multi-index function, usually you can sample as many as you want, right? Because your typical model would be something like that, like a projection, some function. So you have a projection, some maybe nonlinear function on top, plus maybe noise or something like that, right? You can just sample. So you see, like you can learn multi-index model using effectively any method. It's just a question of how much data you need, right? Like you can do one nearest neighbor, it will be fine. It may be exponential. It may be very bad with dimension. So But this one you cannot, right? Like one nearest neighbor is not going to get you anywhere unless you have all of the data. Okay. So first, what is the algorithm implemented by neural network? Is it a low index model? What aspects of neural networks are important? And what are the hidden progress measures? And it was, the finding was, I think, quite remarkable. And it was first made in this paper by Progress Measures for Grokking. They used transform architecture, and they showed that the algorithm that it implements is Fourier multiplication. And let me just tell you what Fourier multiplication is. This is some sort of clarified version of this. So what is Fourier multiplication? Imagine I want to multiply. Oh, okay. First, what is this this matrix? This is a matrix when you put. So take W to be the D's root of unity. So W is so W to the D's power equal 1, and now you put powers. So the first row is 1. The second row is like W squared, W d minus 1. The third row is W squared, W to the 4th, W to the 6th, and so on. So it's a van der Waals matrix, actually. Now, what is, how do you encode now? So your 0 would be encoded. So suppose I want to do modular addition. 0 will be encoded at the vector of all 1s. 1 would be encoded, 1 mod p, would be encoded at the second row of this matrix. 2 would be encoded at the third row, and so on. Now, if you think about it, what happens? So suppose I have the first row that would be 1, and the second row, which would be 2. Now, what is 1 plus 2? Well, what happens if I just take pointwise multiplication of these vectors? So 1 times 1 is 1, so I get 1. W times W squared is W cubed, so I get W cubed. This would be W6, and so on. So you can see I get the third row. So that's the principle. If I multiply pointwise the vector corresponding to the embedding of I and to the embedding of J, if I do this pointwise multiplication, that gives me the row corresponding to I plus J mod P. And you can write it, this is a Fourier, this actually is a discrete Fourier transform. And you can write it as the following. You have 1A and 1B, so you multiply it by this vector to make the embedding. And then the embedding corresponding to A times pointwise the embedding corresponding to B is the same as the embedding corresponding to 1A plus to A plus B mod B. Now I just have to unembed it, so I decode it by doing inverse Fourier transform, which is the same matrix transposed. Okay, that's the algorithm. So you can see this is actually a very clever algorithm. It's really simple, but it's probably not the first thing you would think about. And at the very least, you have to know complex numbers and so on. So Andrei Gromov in this follow-up paper showed that essentially the two-layer MLP does the same thing. The same algorithm. Okay. Any questions about this? Okay. Now I would like to show you that RFM actually does exactly the same thing, and it in fact clarifies many of the issues there. So this is what you get with RFM. This is the number. On the x-axis you have the number of iteration, and on the y-axis you have accuracy and the loss. So you can see that basically the RFM is trained to be perfectly accurate always, so the loss is 0 and the accuracy is of course 100%. After about 10 epochs, there are no epochs, iterations. The accuracy is still trivial, just at a random guess level, and then very quickly it transitions to being perfect. Okay. This is the same problem. Mod, I forget what, mod 61, I think. Any questions about this? Notice the difference. There is no gradient descent. There is no loss function because it's being like fit exactly to the data. And the training loss is identically 0. So the training loss cannot serve as a predictor of anything, right? Because it's 0. That cannot be the hidden progress measure. Oh, hidden or not hidden progress measure. Now the question is, well, what is that thing doing? Like, why? Why is it doing what it's doing? And the answer is, well, we don't know what the mechanism is, but we can kind of see what's happening in the feature matrix. What transformation is it doing to data? And what you see actually is a transformation. Even after one iteration, you can see it starts like following the striped patterns. After 5 iterations, it's very clear, and after maybe 10 or 15 iterations, it becomes perfect. And this is what's known as a circulant matrix. Well, each one of this block is a circulant matrix. Okay, what's a circulant matrix? Now, the circulant matrix is simply the following. You take A, B, C, and you shift it by 1. So when you shift it like this, what do you have? C goes here, so you have CAB, and then you shift it by 1 more, and you have BCA. Okay, that's a circulant matrix. So those matrices are actually circulants. So what it's learning a circulant matrix. Okay. Now, why circulant matrix makes sense for this problem? Let me just give you a very simple intuition. So imagine this picture was also produced by GPT-4, whatever, 4.0. So imagine that this is my encoding of a 0, right? And this is my encoding of 2. Now, if I multiply this matrix, so I think of this as kind of taking Mahalanobis product. It's not a valid Mahalanobis product because it's not positive definite, but let's just ignore that. To make it valid, somehow you have to like play some game with it. But so you can see that this selects the third column, and this select the first element of the third column, so the result is C. Now, if I shift this down by 1, and I shift this to the right by 1, right, so I get 1 in the second place, I get the same result. And that's because the columns of this matrix are shifted. So what is happening is that when I have a circulant matrix and I shift my input to the on the right side down and on the left side to the right, the result stays the same. So that means for modular arithmetic is that the difference in modular arithmetic is actually the same under the separation. So now this Mahalanobis product will give me the same result whenever the difference is the same. So it's implementing modular subtraction essentially. I would have to do something on top of that to actually figure out what the output is. But you can see that that's the right invariance it's learning. For the addition, you would have to switch the diagonals. It would have to be a Hankel matrix, which is the same, but the other way around. Anti-diagonals are constant. Okay, so now we can see, now that we know this is learning a circulant, we can see that the standard progress measures here are all, of course, like nothing interesting is happening, as we have seen until nothing is happening, and then it's short-lived transitions. Same true for accuracy and loss. But now that we know it's circulant, we can actually look how far we are from a circulant. Yeah. Oh, okay. Sounds good. We see how far we are from a circulant. And how do we, like, what's a measure of distance to a circulant? Well, you can just look at the variance along your diagonals, right? Because if the diagonals are constant, the variance along the diagonals is 0. So that's a natural measure. You can maybe weigh it, as we like rescalers. And you can see that from the very beginning, the circulant goes down to, it kind of decays linearly and then goes down to 0. And you can also measure this alignment, which has the same progress result. So we can see that it's literally learning circulant, and you can measure this. Of course, for this measurement to make sense, you have to a priori know that this is what you're learning. Okay, so now maybe I'll skip this. The same thing happens with multiplication, but you actually have to reorder this in some sort of slightly non-trivial way, because multiplicative group is also cyclical, and if you know that, you can reorder it according to the multiplication order. Now, it turns out that if you just do, like, once you figure out circulant is good, you can, okay, let me just do circulant embedding. So I'll take the circulant matrix, and I embed my data using a circulant. And basically, if you do it, you get results which are better than if you try to learn the features. So clearly, like, a priori knowing the circulant is good. Now, what does this have to do with neural networks? Well, neural networks are also learning circulants. And if you look, so these are the AGOP patterns for the neural network for various tasks. But if you actually look at the circulant deviation for neural network, you can see that it's also, in this case, it's actually constant for the first couple of epochs, and then it starts decaying. In other cases, it decays from the beginning. So you can see that as you're training the neural network, the AGOP matrix becomes closer and closer to circulant. So effectively, it's learning the same embedding. I didn't really explain how the circulant relates to the Fourier multiplication algorithm, but it's very similar, because circulant in the Fourier basis is actually a diagonal matrix. In particular, it seems that they've been argued that there are two separate regimes. And in the first regime, you kind of just try to fit the kernel. And in the second part of your training, you learn features. It doesn't look like this is happening for the setlist setups. It looks like features are being learned from the very beginning. I mean, again, this may be dependent on the specific way to set it up, but in this case, features are clearly being learned. Now, you can, like, if you want to stare at what the matrix actually looks for in neural network, this is the weight matrix. So this is W. And if you take W transpose W, you get a very beautiful circulant. And if you take AGOP, you can see it's quite similar looking to that one. You can actually rearrange this slightly just by reshuffling this to make it look nicer. So you can see that there are different frequencies there somehow appearing. Okay. I'm running out of time, so I'll skip this. Let me make one more point, and then I'll stop. First, interestingly enough, there seems to be a big difference between emergence with respect to compute and emergence with respect to the data size here. So if you look at the data, so this, on the x-axis, I have the amount of data, which is a fraction of the full data. The full data is p squared, so this is whatever, like 30% or 40% of that. And you can see that there is quite a sharp transition around 30% in accuracy, right? Accuracy goes from 0 to 100 very quickly as you're giving the system more data. But if you look actually at the square loss, you see that the square loss decreases rather gradually as you're giving the data more data. But this is not quite the same thing, because this is the square loss at completion somehow. And AGOP alignment also seems to increase gradually. So it may be that this emergence is actually kind of different, and in some directions it may be predicted by the standard measures, in other directions it may not be. Okay, now I'll just maybe speculate a little bit. I mean, Fourier multiplication is effectively out-of-domain generalization, right? It learns an algorithm to do this task. Now, can we say that these networks are creative? I would probably say, well, maybe, right? Because it's certainly not the first algorithm I would think of, that particular algorithm, and probably most people would not think of implementing it that way. Maybe you can say, yeah, that's some sort of creativity. And finally, I'll just conclude with the thoughts. So first, emergence is clearly not always predicting by standard measures, so it's not. There seem to be quite different types of emergent behaviors. Clearly, if we don't understand even emergence of representations in something like MLPs, it's very hard to see how can we understand like full computational properties of transformers. And of course, the argument has been made that most of the parameters of transformers are in MLPs in any case. Fourier features do seem to be ubiquitous, and there is some evidence that, for example, pre-trained transformers learn Fourier features for addition. But else work. What process can learn both low-rank matrices and circulant? Very unclear. And I think it is very clear that this generalization out of domain is directly related to feature emergence. And I think I'll stop here.
I think we have time for one or two questions.
These results are about RFM's grokking arithmetic in Z mod P. Do you think it can also grok compositions in any finite group, given in a small finite group?
Yeah, we're looking at this. It's unclear. It's we don't know. Yeah.
So is there any specific reason why you just chose the modular arithmetic example and not?
Oh, that's just because that's what they chose. We've been following up on that. There is clearly nothing special. I mean, you can take some other group, right? You can take a permutation group. And I think there was recently some work that it learned some maybe permutation groups. I'm not
Like
sure.
if you take the symmetric group or the alternating group, would it still work?
I'm not sure. There was some work when they looked at some small symmetric groups, like S5 maybe or something.
Yeah, that was my paper.
Oh, okay, cool. So what was the upshot?
Yeah, so we replicated kind of methodologically the same thing that was in the Neil Nanda paper, and we reverse engineered a Fourier basis kind of defined operation for the group operations. There's actually another paper that does this as well, but they kind of had a couple methodological mistakes and end up with a generalization error where like they collected a bunch of data and came up with an algorithm that was consistent with their data, but it wasn't working for us in other contexts. And we went back and realized there were other algorithms that like were consistent with their data as well, and found a different one that through more experimentation we believe was right. But
Cool. So it works for S5.
yeah, we do A5, S5, and S6, I think.
This is
Very cool. Yeah.
So earlier you said that you don't think norm minimization, margin optimization is the right lens. I mean, is that related? Is that you don't think it's right lens for this part? Because we are able to prove that for certain MLPs, like the norm minimizing solution is the Fourier solution. So what do you think this relates to?
Yeah, I don't know. I mean, clearly they're doing some form of norm minimization, but it's not. I guess what is confusing to me here is like, where is this behavior coming from? Like how, in what way it's minimizing the norm? Like why? Like I don't know what norm this RFM is being minimized.
You know, what direction it's going to.
Yeah,
You can
it's
actually prove that the norm minimizing solution for
it is Fourier. That's that's a really good result, but it's somehow I don't think it explains what's happening fully. It's because like why is it like what exactly is finding? I mean, yes, there is some implicit bias, and probably neural networks are doing something like that, which I guess is not completely clear. But how? I don't know. Like I think that the picture is still very unclear. We can talk about that offline.
yeah. I guess following up on what Ben said, I mean, also share the sentiment is, are you claiming that you have evidence that this is not happening, or are you saying that you're not, you don't have evidence of this. Because, I mean, the thing is that this is definitely mechanism. We say, well, what's the implicit bias? How is the optimization causing it? Even if we don't know how to answer these questions, we know that in principle, we understand mechanisms where this might happen. And so the fact that we can put our fingers in it doesn't mean, I mean, in this particular setup, doesn't mean that that's not what's going on. So I'm just trying to, again, do you have evidence that that's not what's going on, or you're just not finding the evidence that it is going on?
I don't find, I guess, I think this is suggestive, and I think definitely I don't disagree that this is like closely related to what's happening, but I don't find that there would be a full explanation for this. In particular, like why does RFM, like it's not clear to me like what norm it's minimizing, right? It's
I also don't know what norm is being minimized by, like, you know, ResNet with all kinds of convolution and stuff like that. And it's pretty clear to me that something is. So, I mean, the fact that we can't like exactly describe it.
That's fine. Yeah, I think we just need a much tighter connection. I think because we see that this phenomenon seems actually you can get it for like other architectures as well. So it seems like there is some sort of universal phenomenon. Do all of the things minimize the norm? I don't know. Like I do like ML whatever the transformers when they learn like non-modular addition. Is it the same thing? It just there seems to be some very general thing. And somehow it's not completely clear how to, like, for example, what is really unclear to me is, you know, when the loss is zero, where is norm minimization coming from? What's loss is like close to zero. Like this is for neural networks, so loss is not exactly zero.
It can go in the direction.
Yeah, but for RFM, it's exactly zero, right? So you have some other thing. Is that what? I guess I don't understand what the fundamental mechanism, right? It's, but NATI is not satisfied.
Well, just the fact that we, the thing is, again, there's this distinction between we don't understand it and it doesn't exist. Because, like, even go back to boosting.
No, but I don't say it doesn't exist. If I give an impression that it doesn't exist, that's not the impression I want to convey. I just think that there is something quite strange going on, and we don't have a full explanation. And it's rather fundamental, it seems.
Okay, well, on that note, let's take a break and let's resume at 5 minutes after the hour. 3:05.